Git creates a blob for every version of every file in your project. But blobs don't know about paths, file names, or permissions. Blobs are just that. They are just blobs of content floating into space. What ties everything together are trees and commits. Just like files are represented by blobs, directories are represented by trees. Simple. The root of the project is a tree too, by the way, because of course it is a directory. So what's inside these tree objects? Well, let's zoom into this root tree here. A tree object is a simple list of the contents of one directory. Directories can contain files and other directories, so the first bit of information listed is the type, which can be blob or tree. File name, checksum, and mode are also listed. There's a separate tree for each directory in the repository. So if we look at this directory over here containing a single file, Git stores it as its own tree, listing only that single blob. Then when you do a git commit, Git creates these lists, calculates their checksum, and stores them under the .git/objects directory side by side with blobs. When looking at the content of this directory, blobs and trees look just the same. A compressed file with a weird name. Let's expand these trees again. To give us some space, let's omit the mode for now. Also, the type can only be blob or tree. Since they're also color-coded, let's remove that too. So now we can clearly see what the tree is doing here. For each entry, we have the name of the file in the working tree and how it maps to an object checksum in the repository. Now let's rearrange this a little, and let's also add in the blobs. And let's add some arrows to reinforce the fact that trees point to other objects by their checksum. Well, this is my mental picture of how Git objects are organized into space. But it's quite simple, right? A tree is a list of the things that are inside a directory. But this implicitly hides something really nice. Let me show you. What happens if the contents of the file in this tests subdirectory changes? Well, the checksum of the file also changes, so Git creates a new blob for it. So far so good. Then we need to plug this new checksum in its parent tree. And we have a different tree all of a sudden, with a new checksum for the directory. Then we need to plug this new checksum in the root tree, and we have a different tree again, also with a new checksum. This is really cool. What this means is that if any file anywhere in the project changes, the way checksums cascade all the way down to the root tree means that the root tree checksum will also change. So if any file changes, you always get a new root tree. How cool is that? So if we modify this file over here under the root, we get a new blob with a new checksum, and that generates a new tree. Notice that this tree still points to the previous subtree because that hasn't changed, so we don't need to recreate that. So now you have this one checksum for the root tree that represents an entire snapshot of your repository. It is enough to have the checksum of any of these root trees here that Git will know how to check out these files to the working tree. And how beautiful is that? An entire snapshot of your project summarized into this one little checksum for the root tree at that point in time. That is super cool. So now that we have reliable snapshots well summarized, it's time to tell a story, and that's done with commits. A commit object references one root tree object. But what is special about commits is that they also have a reference to their parent commit, or their parent's commit in the case of a merge commit. So now we know where we are and where we came from. We are at this tree over here from which we can trace down the full content of the repository. And before this, we were at this other tree, and before, and before, and before. Commits bring Git repositories to life. They tell the story of the project. So that's why commit objects also contain information about the author of the commit, date of creation, and of course the so important message that tells you about the changes that were done in that commit. But now that's enough motion graphics. Let's take a look at these things working in real life. Let's create a repository and do what we do things for real. Let's go. Okay, so I have an empty directory here, nothing in there. Let's initialize a Git repository in here. So git init-b to start at the branch main. So now we have this new .git directory, and that's what git init did for us. If we see what's inside .git/objects, for now it's pretty much empty. It only has these 2 subdirectories that are also empty, but we're going to start monitoring this. And we're going to do this with a little utility that I have for myself called cmdiff, and do the same command that we just did, tree.git/objects. All right. And this inside our VS Code opens this diff view between the previous version of the contents of the directory and the new version of the contents of the directory. Don't worry about that. You're going to see this in action in a second. I'm going to open a terminal in editor area. Did you know that you can do that? Because this is a little bit easier to shove around. Open it at the bottom here. So now let's create a file. Let's create a file like this. Let's do code and the name of the file, say file1. As usual, super creative. And we shove this file at the bottom here and to the left. Cool, now we have the terminal to the right and the file to the left. Let's put some content in this file. Let's say some content, whatever. Save the file and go back to our terminal on the right here, and let's do a git add file1. Now we're going to see something happen in our repository up top there. There you go. A new thing appeared in our objects, and that is, of course, a blob, as we saw in our previous video. Notice also that we do not have trees yet. Trees appear when we do a git commit operation, okay? So let's try that. Let's do a git commit, and let's put a message here, initial commit, okay? Really simple. Let's try to think what happens here. We should see the commit object appearing because we are creating a commit, but we should also see that root tree appearing because the commit is going to point to the root tree. Let's see that. 2 new objects should appear. Boom, there you go. This one here, 9a, f9, f6, blah, blah, and e5 to e84. Now the contents of this directory here is looking a little messy. There is no way for us to tell the difference between these checksums just by looking at them. We need to investigate what they are. So to differentiate between these, what we do is cat file -t for type 2e f267e. Boom, the first one is the blob that we already knew. And let's go for the next one. Replace this by 9a f9 f6. That is our git commit object, so we know the last one should be a tree. Let's make sure that that's correct. So e5 to e84ff. There you go. That's a tree. So now we can start looking what's inside. And to do that, instead of using the -t flag to this git cat file command, we use the -p for pretty, for print, or for pretty print, whatever you prefer. So let's go here and replace this -t by -p. And let's see what happens. What is the content of our tree? Ooh, here we have 100644, that is the permissions. And then we have this blob word indicating that this tree contains a blob. The checksum of the blob is 2EF267. Whoa, recognize it? This is the blob contained in the tree. And then the file name. The original file name here, expand this a little, boom, file1, there it is. Brilliant. So if we want to get a little bit more advanced even, well, let's create a directory. Let's make dir, let's create subdir, that's the name of our directory. Now we create a new file called subdir/nested file. And let's say that this file has some other content. Save it, git add subdir/nested file. Well, git add dot would have worked as well, but let's be very explicit what we're doing here. We should see a blob appearing. So one more object should pop up there. Let's see. Boom. 7280A7, blah, blah. We know that that is a blob. So let's do a git commit with a message. Second commit. Don't do that. Okay? Do very good commit messages. For now, let's see what happens. Let's think here. What should appear in our git/objects directory? Well, the root tree, okay, because we always get a new root tree when we do a commit, and we should also get a tree for this directory that we just created. So we should get 3 new objects now. Let's see them appearing. Boom. There we have it. 5917, 8362, 8D, C5. And then you can go and explore what these are doing, and maybe we should find a commit here and see them pointing to the parent. Let's go. So an easier way of tracking down what these things are doing is, of course, using git log. Let's do git log. And now we have which one of these are the commits. So this object over here, the 8DC527, that is the commit that was just created. And then if we inspect this commit, so git cat file, 8DC527 with the flag -b, there we have it. The tree, the parent commit, the author, the committer, and the commit message. If we want to inspect the tree, all we need to do is to inspect this one here. So let's see, git cat file -b 5917 6f. Well, there we have it. That's the content of our new root tree. It contains a blob, it contains a tree with these permissions, with these checksums, and with these file names. And I guess by now it was plenty of examples on how you really dig into these structure and dissect them by yourself. And that is it for me today. This is one of my first videos, so leave a comment, leaving some feedback, what could be improved, or if you enjoyed the video, if you found it informative or not, or if you have suggestions of other things that you think I should be talking about. Yeah, that's it for me today. See you in the next video. Hej då!